Hello, everyone. Welcome to today's webinar. We're going to do a webinar talking about how to perform measurements with VISCO. It's a really packed agenda, but this time we're going to make up time. So just a bit of housekeeping on the beginning. Session will last for approximately 1 hour. 45 minutes of this is going to be the presentation, and then after that we'll have time for questions and answers. So if you have any questions during the presentation, there is on the webinar browser, there is a box questions. Just write down whatever you want to know. I think imagine lots of people will have lots of questions. Just write down. We are going to cover them at the end. For this session, everyone will be muted, so it's just going to be my voice. And this webinar will be recorded for the future, so you can watch on demand as well. Please note that as this is going to be recorded, all the participation, everyone is going to be recorded, and so you're receiving the rights to this participation to us. So just presenting who is with us today. My name is Bayard Morales. I'm going to be chairing this webinar. I'm the marketing manager for multi-visual inspection and evidence. And with me, as part of the panel, is Yaroslav Tom, who is going to be helping me with the questions. Right, so let's get started. Packed agenda, 5 different chapters of this. Let's get started. The first thing that we're going to do is a quick review on the borescope technology, so everyone is in the same page. So borescope is a generic term for industrial endoscopes. Right? So there are different types of borescopes, different types of endoscopes. Generally, we classify them between rigid borescopes, fiberscopes, and videoscopes. And the main difference between them is the rigid borescopes, as the name already says, has a sorry. Can you guys see my screen? Right.
It's visible. Yes.
Okay. Thank you. So on the rigid borescopes, of course, the probe is rigid, and the fiberscopes and videoscopes, they have flexible probes, generally with interchangeable optical systems. The technology, of course, started with rigid borescopes, but nowadays most of the work is done with videoscopes. One thing that we're going to hear all the time in the industry is the term borescope inspection, and the acronym is BSI. And borescope inspection might employ any type of endoscope. Right? So when you say borescope inspection, doesn't mean necessarily that you're using one or the other type of equipment. This slide here shows a really summarized presentation of the difference between the systems, between rigids, fiberscopes, and videoscopes. Not going to go into detail very much, but the main point is that most of the work for borescope inspection nowadays is done with a videoscope, and really because they are much more versatile and easier to use, and the image quality is really high. So most of the time, really, we're going to be talking about videoscopes. When it comes to videoscopes, we have a large range of products on this. Each of these products, they suit a different type of inspection, different type of requirement. So on the left side, you have products like iPlex, G-Lite, GT-GX, and NX, which these are considered, let's say, general purpose videoscopes. They can do many different types of inspections. And on the right side, you have products like the iPlex TX, which is a very thin videoscope, 2.5 millimeter probe. And you have the iPlex GR, which is an extra long, up to 30 meters long videoscope. Most of what we're going to see here today is going to be looking at the main line, the most general purpose videoscopes, which you will see on the left side. So videoscopes can do a lot of different functions when we're thinking about borescope inspection. It's not only about seeing and visualizing things, and the good example would be a videoscope like the iPlex with a working channel. So a videoscope like that can provide images, so you can see things, capture images, and record videos, which is qualitative information. You can also perform measurements, and that is quantitative information, and you can perform some remote operations. On the case of a video scope like this one, you have a working channel, so you can retrieve objects from inside the inspection area. Each video scope will have a different suitability, and today what we're going to be talking is about measurement. So now I'd like to, since now you know what video, what the borescope is, I would like to ask the audience, what is the type of equipment that you use the most between rigid borescope, fiberscope, and video scope? Yaroslav, could you please start this poll? So I'm going to ask you to vote on this poll. I think now it's open. So if you can select what is the type of video scope that you use more often, let's say that I'm going to give you maybe like 30 seconds to vote. Let's see. So apparently most of the people use video scope. So far nobody said that use rigid borescopes. They still have a use. So let's give a few more seconds to the voting. People are still voting. And Yaroslav, let's close the poll and see the results. Thank you very much. So you should have on your screen now the results. Well, we see 67% use video scopes. 19% do not use borescopes. So welcome to this presentation. You're going to see something new today. And the rest use fiberscopes. And as I see here, no one voted for rigid borescopes, which is very interesting. It doesn't mean, I think now actually you guys seeing the poll results. The fact that nobody said that use rigid borescopes doesn't mean that they are bad, but it's less likely that people are going to use. So let's continue with the presentation. Thank you very much, Yaroslav. Now, before we move into how to perform measurements with a video scope, I would like just to speak about some metrological concepts. And that's very important because when we're doing a visual inspection, it's one thing, but when you go to do a measurement, it's different. On a visual inspection, like for instance this one, we're looking to the quality, the condition of a weld here, for instance. We're looking for the presence of defects or shapes, colors, or the presence of debris in the region we're inspecting. So this information is what I call qualitative. So we are getting a description of what we see. Now when we move towards measurement, and in this example here, we are measuring the excess weld metal height on a weld, you're talking about numbers, sizing a defect, sizing a feature, distance between parts, and so on. And this information is quantitative. Big difference there, because the answer that we have, the output that we have, is not a description, but is a number. And when there are numbers involved, we have to talk about error, accuracy, and uncertainty. So if you do a measurement using any instrument, either a borescope, a ruler, scales, any measurement, you're going to have the value that you measure, you're going to have an associated uncertainty with the value that you measure. That means that an estimate how wide is your error range, and you have probability of the true value being within that range. We are not going to cover in detail here the probabilistic part, but we're going to take a look on the measurement, how to produce this number, and what is this uncertainty. So our job when we're performing a measurement is to get as close the real value, the true value, keeping the uncertainty to a minimum. Right? So that is very important. In practice, all the measurements that we do with any instrument should have an uncertainty statement. Where does the uncertainty comes from? So there are many sources possible. Each type of instrument will have their own. But when we're doing measurements with video scopes, there are particularly 3 sources which are very important. The first one is the equipment itself. So if we can select the equipment that has suitable measuring capabilities, that's point 1. The second point is the measurement procedure. Having equipment that works, but a procedure that's incorrect to measure what we want doesn't work. Now the third thing is the operator skill. These equipments, they require a trained person to operate. If the person who is doing the measurement doesn't understand what they are measuring or doesn't know the technique, the measurements will be wrong. Even if you can produce them, they will be incorrect. So these are the 3 main sources of uncertainty when we are doing measurements with scopes. Another concept that is important is the other 2 concepts is repeatability and reproducibility. They sound the same, but they are not. When we're talking about repeatability is if we have exactly the same equipment, same procedure, and same person doing the measurement, are the numbers, the measurements the same? This is a repeatable measurement. Now, if we're talking about reproducibility, is when we change one of these factors, any of them or all of them, do we get similar values of another method? And the importance of this concept, this concept is particularly relevant when your measurements are under dispute. Let's say, for instance, if your company, you're doing a borescope inspection, you measure something, and someone says, no, I don't trust your measurement is correct. How can you ensure, how can you guarantee that your measurements are reproducible? If the company if your customer tried to measure the different method, do they get the same value? We're going to see a few things that we can do towards that. The other 2 methodological concepts that are important is documentation and traceability. So documentation is to prove that it's a recording of the measurement that show that has been done properly, and you can track back to the procedures and the training of the people. So documentation is, yes, you have the documentation of how to do the measurements. You have the files that you created, so the image with data and measurements, and you have training documentation. This point is particularly important because, for instance, it's very common that you're going to find, especially in aircraft manuals, that you need to do a specific measurement, but they don't tell you the method. And this is something that falls to many customers to define their own processes. And important that this process actually exists. And the traceability is not really documentation, but it's the ability to track, to link your measurements to a reference that is calibrated. And the importance here is if you do a measurement with a video scope, how to prove that video scope was working correctly and it was tested against a calibrated reference. We'll come into more detail soon. Now we jump into the stereo measurement methods technology, right? So this is the technology that we have implemented in evident video scopes for performing measurements. And this technique resides on the idea of parallax. So the image here that you see on the right side, imagine that essentially you extend your arm and you put your thumb up, and then you close your right eye and you look just with your left, like this, and then you do the opposite. Close your left eye and you look just with your right eye. Keeping your thumb and your arm extended, it will look like if things moved on your field of view. But that's of course not true, but that's what we call the parallax, this apparent movement. So this lateral shift is the apparent movement. And when you have this shift and you know what are the optical properties of your optical system, you can then compute points in space and can perform a stereo measurement. So this, for instance, is just the types of lenses that we see. Like these are lenses that are for stereo measurements. For instance, you can see more or less here that they have 2 cameras. They have essentially 2 optical paths. Here, this image shows a little bit more into detail what actually happens. So this representing here is the optical tip of the video scope. And what you see here are two different optical paths. So you have two lenses on the probe. The light that comes here hits these lenses, and they are capturing different parts of the sensor. So what happens then is you're going to have two images, one of the side of the other, and the algorithm will map the points from one image to the other. So when we select the points in the image to perform a measurement, the software will automatically know what is on the left and what is on the right side. And that will allow them to create a map, calculate points X, Y, Z, so three-dimensional measurement in the whole image. So once these coordinates are computed, we can perform measurements. Everything that I described happened automatically behind the scenes on the video scope. You don't need to do that part by yourself. That is all done by the software. And here I'm going to show you a video that shows exactly this happening. So this is a stereo measurement. You're going to have a left lens and a right lens. Both lenses are looking at the same object. So that's which will allow me to perform measurements. And now we're going to see how this happens. I'm going to play this clip. So the first thing I would like to point is you see here a cursor, right? So this is the cursor of the points that the user is going to select. Here we're just doing a simple distance measurement, right? As we are going to move this cursor, we move the cursor on the left side and the right side moves automatically. So let me play a little bit more of the clip. Now the cursor is going to move, and you're going to see that the right side will automatically be dragged to the right position. So once the user selects a point on the right side, on the left side, we can see that there is an X, and that shows like the point was selected and it was matched on the right side. And then I can continue selecting the points. So you can see here the user selected 1 point, 2 points, and then you have the measurement, in this case 2.25. So that is the essence of how the stereo measurement works. You're going to work on your left side selecting points. The software automatically matches these points on the right image, and then based on this, you're going to have measurements. So now the second poll, again, I'm going to ask Yaroslav if you can start this poll, is how often, if you perform measurements, how often you perform measurements with that. Right, so let's take a look here, because one of the more challenging things of measurement is that people don't do very often. And when we don't do it very often, we can forget things. So we, as manufacturers, we spend a lot of time, we invest a considerable amount of time getting people trained properly on the methods. So let's see, we're still waiting for votes. Let's see what else people say. Let's give 5 more seconds and we close in a bit. And Yaroslav, if you can close the poll, thank you very much. So interesting enough, right? Most of the people who voted, 43% say they do weekly or more often measurements. That would be a very frequent use of measurement methods, so that's interesting. And I think the tricky part is when you do, for instance, 22% say that they do it monthly, and then the other 13 few times a year. So on this case, it's very easy to end up forgetting what we need to do. Hope this presentation will actually remind you of your points. And well, 22% have never done a measurement, so hope you've seen something new. Thank you very much, Yaroslav. So now we keep going. Now let's look a little bit on the recommended practices. There is here a generic step-by-step process for measuring with video scopes. Right? This is a generic. It would probably suit almost any type of measuring process. And what we're going to see is how to prepare, how to perform the measurements, and how to finish our measurements. Here I'm going to show the list of steps. I suggest it's a 7-step, right? It looks like a lot. It's not. It's just really like here I'm trying to break down what people really should do. But bear in mind, the preparation stage is something that you do once in the beginning of your inspection. So let's say you're doing inspection and then you say, oh, I need to measure something. You would follow these steps 1, 2, 3. You would do it once before starting your measurements. Now, when you're going to do your measurements, then you go step 4, 5, and 6, and these you repeat as many times as is required. So if you have, let's say, if you're inspecting turbine blades for defects and you rotate the blades and you have defects 3 or 4 blades, you're going to do this 3 or 4 times. And in the end as well, that is a last step, is to check the video scope after your measurement is still working as it should, just to avoid the situation that maybe you damage the video scope during the work and it's not working. We won't have the time to go step by step. Actually, there are even other webinars that we go more into detail, but there are 2 steps that I consider critical that I want to cover in more detail. And one is the final step of preparation. So the step number 3, verification of the accuracy. And the other one is positioning the probe. So about high verification of accuracy. Before you're going to do any measurement, is absolutely critical for a person to check if the video scope is working as stated by the manufacturer. This is something that's not only for our video scopes, it's for everyone's video scopes. And pretty much any measurement device, you should do this. For the video scopes, the way this is done is using a tool called check tool, right, which is a very simple device. This check tool, however, has a set of reference features. Right? There's something that we're going to be able to measure that, and the distance of these features, they are linked to a calibrated standard. So when you're doing this, you're checking mainly if the video scope is working correctly, if the setup is done properly, if the optical tips are working properly, if the software properly, etc. And I would say the use of this check tool is probably one of the simplest way to save time on your measurements and make them more accurate. You always should perform this check before starting your measurements. Not everyone do it, but then you're always under the risk of actually making a measurement that is not correct, and you don't even know that. So the answer for when you do this check is always before starting your measurements. Now what we're going to see is what actually this check means, right? So what we have here on the screen, this is an image from the iPlex G-Lite, or handheld video scope. So this is the image from the video scope itself. And here is how is the position of the probe. So that is on this check tool, there is a hole that you put the probe there and you see something like this. I'm going to play a short clip here. So what you see here is the image from the video scope directly inside the check tool. And what you see there is, it's just a plate with holes drilled at different distances. And the special thing here is that the distance, these holes were drilled in a specific distance that was measured with very high accuracy. And this measurement is done with an equipment that's calibrated to international standard. So what we do here is we're going to measure the distance between 2 points, and this distance has to be really close to what is stated on the manual, or there is a small label on the check block. So what we see here is the user selecting points, and then you select 2 points, and the measurement that the user got here was 2.01 millimeters. If we go in, if there is a label on the check tool and if that states that the measurement should be 2.00. And that means that this measurement is within 1%, is well 0.5% from this table. That means your videoscope is working correctly. So this check that takes really 30 seconds to do can make or break your measurements. So always, before starting doing measurement, do a check of your videoscopes. All videoscopes that do measurements, they should have these reference tests, these reference procedures. So when we do this accuracy verification, we get two things done at once. The first thing is that we are validating that our videoscope measurement function is working correctly. And I have to repeat, which is how important that is, because if you don't do this, you might get results that you have no idea if they are correct. And the second thing that you do is when you do this, you're linking the measurements to international standard. The reference block is a calibrated tool. There is no way to calibrate a videoscope to always be right, but when you do that, this check, using the calibrated check tool, you're making sure that your videoscope is as good as it gets at that point in time. So that's very important to do. And we always suggest when you do this verification, save a picture for reference, because you always can prove that your videoscope at a specific time was working correctly. So just for reference here, on this table, you see the accuracy that is expected in different videoscopes from Evident, from older models to the newer ones, and you see how the accuracy has improved over time. And we see like the iPlex X has a really narrow accuracy, so it's best accuracy, and you have iPlex, G-Lite, and GX with slightly higher band of accuracy. This type of information should always be provided on the manual of the equipment. Bear in mind that if the equipment is working within the accuracy, it doesn't mean that all your measurements will be within 1%. It means that the baseline of accuracy is 1%. Your accuracy will always going to be lower, but that is because of the nature of measurements. Process and skill of the operator, they play a role as well. So the other very important step is positioning the probe. One of the most important things in positioning the probe is the distance between the optical tip and what you're measuring. This is called tip to target distance. And it's very important if you want to do a measurement, each videoscope has a specific range of distance that you can measure. So, of course, like depending on what we're measuring, we're going to be farther or closer to the surface. And when we're moving the probe around, we're playing with three different factors, which is the first is the distance. Right? So the farther I am from the inspection region, the bigger the area I can see. But the trade-off is that potentially the accuracy can be lower. And this happens because the farther away I am, the longer the distance is, everything looks smaller on my screen. So I have essentially less resolution of the defects. So the rule of the thumb for positioning the probe is 1. You can only measure what you can see. So if you want to measure something that is very small and it looks very small on your screen, it's difficult to measure. If the defect is really small, try to get closer. So with this, it's very simple to understand that if you want to measure something, make it a decent size on your screen. Now, for instance, to estimate what is the right distance that the videoscope is, the distance, there is a function on the iPlex videoscopes called spot ranging. This function provides an instantaneous estimation of how far you are. And that gives you an easy guidance to know if you are within the range for the measurements. For instance, here, when you're doing this, when you activate this spot ranging, you're going to see on your screen something like we call it the color range. And that gives you an idea what is if you are within the recommended range. It will be easier when in the next slide we'll see a bit of a video, but it's interesting to see that the IPLEX NX is the one that is going to have the largest recommended range of measurement. So you can get defects that are quite big, so you have to go a bit far, and you still have within the recommended accuracy range. For the other videoscopes, this range is slightly shorter. So if you really want to have the best measurement capabilities, you're probably looking at something like the NX. And also you're going to see when you do a measurement that the red areas, these are the ones that we don't recommend measurement. Measurement it might be possible, but you might have the accuracy compromised. The yellow range is an area that you still can do measurements, but your accuracy might be compromised. So on the NX, just coming back, the idea that you can measure from far really is to provide you with a enhanced increase on the measurement area. So as you can see here on the image here on the left side, the area that you can measure, the diagonal of this area, goes with the square of the distance. So because the NX has a recommended range that is twice as big as the other videoscopes, the area that you can measure with the NX is essentially 4 times as big. So this is something that might be relevant for some applications, especially when you have like large graphs and you want to capture things just in one go. NX with a longer range is something to be considered. Now, the other thing as well is that using stereo measurement, you can measure from almost any angle. And this is a common misconception. Many people believe that the probe has to be at 90 degrees from the object, and that is not the case. In fact, if your probe is straight towards the surface, you might have a bit of glare, and it might be difficult to see what you want to measure. And here I see there is an example here. This is a defect close to a root of a blade, turbine blade. And this is when we have the tip, the optical tip, 90 degrees to the blade. And this is where we have just changed the angle of attack a little bit. And the main point here in this image, you have a white zone, which is not great for measurement. You have glare here. And on this here, you have a more image with better contrast. So it's better to measure on this than in this one. So if you have lots of glare, try just to move the probe a little bit. The other important thing is coming back, you can only measure what you can see, and you have to be able to see both on the right side and the left side. So for instance, on this case, let's say that I want to measure something, I don't know, like the length of this section here. I can see it very well here on the left side, but I cannot see that same part here. You see that there is a gray square on the right side. If I want to measure that, it should be inside this. So you have to frame whatever you want to measure, you want to frame that to be as close as the center. So that's why this is all showing as red, because you don't have matching points here and there. So if it's not on both boxes, you're not going to be able to measure. So you want to put the fact or the feature you want to measure on the center. So now let's look into a few selected cases, right? So the idea is let's put in practice what we just saw, and let's look some measurement cases. This is a classical case that we're seeing here. So this case is it's just defect damage on the turbine blade, and this is being measured with an IPLEX G-Lite. We are going to use here a method of measurement called point to line. As you can see here on the image, we're going to create a reference line and then measure a third point that is here. And what we're going to see here is we're going to see the spot ranging in action. We're going to see the stereo, what we say, like you select a point on the left side and match on the right. you're going to use multiple measurement points and make some observations of how to position these points. So let's take a look here on this video. So I position my image. The first thing is, yes, I see the fact what I want to measure is big on the center of my screen. So position is really good. I press the button measurement. And the first thing that we see is the spot ranging function, right? So what you can see here on the center of your screen, this is the spot ranging function in operation. So for each point that I select on the left side, I'm going to have a value z, and this is the distance between the optical tip and the measuring surface. And here I have a graphical representation how far I am from my measuring object. So moving the cursor around, you see like different points will have different measurements. But I am in the green zone for most of the points, so I can proceed to my measurement. I'm going to press measurement. And then I'm going to select the point to line method. Now this method, I'm going to select 2 points. I select 2 points across the defect that I'm measuring. And here again, another observation, which is when you're selecting points really close to the edge of the turbine, avoid selecting right on the edge of it. Because what happens is sometimes you cannot see, but you might be selecting something on the background, and then your measurement is not correct. So instead of trying to be ultra precise here, you can just put the point roughly on this area, and this will have very little influence on the final result of your measurement, but will make you less likely to make a mistake. So let's keep going with video. I select 1 point on the right side and another point on the across the defect. And then I can select up to 3 measuring points here. So when I finish this measurement, I have a very good characterization of my defect, and I can take a decision about the size of this defect. And then I select here the 3rd point. So I have, in the end, 3 readings for the value of this defect, and this gives me a good idea how big the defect is. So another example that was very interesting was this case here. So this case is quite complex. This is an image taken from inside a pipe that suffered cavitation. And the question the customer had was, what is the deepest point of this cavitation damage? For this one, we use the iPlex NX. It's a quite complicated image to capture. As we can see, it's not easy to understand what we're looking at. And we use the depth measurement. So what I would like to mention here is this was done using a 4mm video scope. Generally, the 6mm will be easier to measure with, but the 4mm can do an excellent job as well. This one is also interesting to see such a complex geometry, right? That we're going to take the image, and still we're going to be able to do a good measurement. And we're going to see color maps as well. Oh. So let me play this clip here as well. So on this case, I have already selected my points, my reference points. This is the depth method. So I have 3 points, and the next one will be the measurement. I can see I am within the recommended measuring range, which is good. But what you see here is that's very difficult to select what is the deepest point here. It's difficult just with the optical image to see that. And that's where the 3D modeling plays a role. So on the right side, what we have is, oops, I'll just go back to the video. We have a representation of this surface here, right? So based on the stereo image, the software creates a model, a 3-dimensional model of that surface. And then from there, it's much easier to understand where is the deepest point. So now when I go selecting the points on my left side, So I have a point selected there. I can see it here, right? So I'm mapping this point here on the 3D model. What I can do as well is actually use a color map to show me what is the depth of each point compared to my reference plane that I have here. And then this way it's much easier to understand what is the deepest point against that reference plane. So another case of application here, and this is an interesting case because it was a real case with the customer. It is to use the 3D model to correct a mistake on stereo measurement. This one is done with X and X. And what we're going to see here is to remeasure an image that was taken previously. Right, so this was done, it was already saved the image, and we are remeasuring it. And we're going to see a few techniques here, placing points on the edges and the zoom and the verification using the 3D model. So the image here is saved. Right, so it's not something I'm doing live, it was already saved. And what the customer wanted to do here is to try to measure. This here is again, is a fact, plate root, if I'm mistaken. It's to try to measure what is the depth of this against the front of the plate. So it's the image is quite tricky. You cannot really understand just from the image where you're putting the points. But once you're going to do the remeasurement and you load the measurement, you see what is the value. You already see the points the customer select, and you see the values. Now what we do is to activate the 3D model to see where the points are in space. The initial value measured was 1.3 millimeters. Now when we see on the 3D model, what we see is that the reference line is actually complete out, it's away from our blade. So these points here, they should be much closer to the blade. So what I'm seeing here is, although on the image it looks like the points are in the right place, the 3D model showed me that they are not. And this might be the difference between rejecting or keeping an engine on the wing. So once we did this, we did the stereo measurement, we can go and redo this measurement now, using the 3D model to confirm our measurements. So I'm going to erase here completely the points, and I'm going to redo this. I'm going to jump a little bit faster here on the screen, but I'm going to redo this measurement. Now what we see is that using the 3D model, I can see in space where these points are. And that is the great value of the 3D modeling. It's not that we're doing measurements here, but we are checking, all the information is on the stereo image, but we are checking here if my points in space are in the right place. So that is the model is a verification tool that helps you to avoid mistakes. So in the end of the day, instead of 1.3, the measurement was much more close to 1.5, 1.6. And that was the difference between rejecting and accepting, keeping the engine. So that is the sort of resource, the sort of benefit that the 3D modeling has. So closing pretty much on time, just the summary here, the takeaways for you guys to remember is, if you're not familiar with scopes, they are really versatile tools. Main functions is taking images and videos, doing measurements, and removing foreign object debris, manipulating objects. Every measurement that we do, no matter how good we are, there is an associated uncertainty. And what we can do is to try to reduce that using the right video scope, having a proper measurement procedure, and making sure our inspectors are trained. To make sure that your video scope is working right before measurements, always perform the accuracy check. There is one thing I want you guys to remember is always perform the accuracy check. And finally, the right position to measure is one when you see the feature or whatever you're measuring clearly on the screen and the probe is within the correct measurement range. That is the presentation. I hope that this is useful for you. Of course, there is much more detail, but this is just a summary. So first, I would like to thank you, everyone, for your attention.